3.5 years ago, I've recorded this video here, one of my very first. In a nutshell, I've connected two capacitors in parallel, and then we have seen parallel resonances. This time I would like to make a similar experiment, but I've soldered 2 times the same capacitor, the 100 nanofarad capacitors, in parallel. Now we have 200 nanofarads. And the first thing we've noticed is there is no parallel resonance here. We can see the 200 nanofarads because the green line is now shifted to lower values. But we also recognize that our resonance frequency shifted. We can use another marker and let's search for the minimum value. And our resonance frequency is now at 26 MHz. Okay, next experiment. This time I have just relocated the same capacitor from here to here. So this is the same capacitor as before. And let's check what result we will now obtain. We obtain a different result. It seems that the green and the orange trace, they are quite similar at the low frequency regime, indicating that the capacitance value is the same, 200 nanofarads. But then we can see here 3 different resonance frequencies. It depends on the inductance. You can see here that the green trace show way more inductance than the orange trace. And the reason is just how our capacitors are located. Because with this experiment, the magnetic field caused by the test signal from the vector network analyzer gets accumulated from both capacitors. And in the previous experiment, the magnetic field was cancelled out. And if we can now select between green, turquoise and orange, I would definitely select the orange trace because it shows the least inductance. Next experiment. The capacitance value changes with voltage for class 2 capacitors like those using an X7R dielectric. And we can check this phenomena by biasing our capacitor now. For this, I have 2 so-called bias T's. So our bias T is connected here to our DC power supply, and this voltage is then supplied here to our device under test, to our capacitor. And here in between there is an inductor, but we have used here resistors. And here to the path to the VNA, we have a DC block. So now let's repeat calibration, but with the bias T here in between. So again, we go on cal, start calibration, through open short match, next, select the ideal kit so that we get our calibration plane again here at the end of our trace, and then let's start. Okay, calibration finished. Let's check whether our calibration plane is located here at the end of our trace by using the ideal kit and without any offset correction. And yes, S11 shows us again that most measurement points are here located close to the open point in the Smith chart. Okay, this is our test setup. Here we have port 1, then the bias T, then here we have our 200 nanofarads device under test, second bias T which directs here to port 2. And now I have here my power supply, and I will increase the voltage now, and then we check how this impacts our impedance curve. And you can see the higher the voltage, the less capacitance value we see here, resulting also in a shift in the resonance frequency, but the inductance value stays the same. In simulations like this, you have here your nominal value, and then let's assume we lose 20% of capacitance. So then you can see the orange curve is now shifting here on the low frequency region to higher values, so higher impedance. And now we have 40% less capacitance, or even 60% less capacitance, which results then in this curve here. So you can see the higher frequency range is defined by the ESL and stays approximately the same, whereas the lower frequency range changed a lot due to the change in capacitance. For the end of this tutorial, I would like to show you a cool miscellaneous feature of this VNA. it can calculate the TDR, time domain reflectometry. So it's not the true native TDR, but it can calculate the inverse Fourier transform of S11, taking the real part of it and integrate it to emulate TDR. For this we start calibration again. I would just press on preset so that we can start from scratch. Okay, I'm trying to get the full range of our VNA. So I'm starting at 265 kHz and stopping at 26.5 GHz. I've changed the number of measurement points to 100,000 with a step size of 265 kHz, resulting in a linear sweep with equal distance between each measurement point. So we are starting at 265 kHz and after each 265 kHz with the next measurement point. But we can see here that our sweep time increased to 21.7 seconds. This is too long. Unfortunately, I have to decrease the bandwidth of our intermediate frequency filter to 100 kHz to get the sweep time down to 2.17 seconds. And now let's start again with calibration. Start calibration. This time I'm only interested in a one-port calibration with open, short and match. And I'm using the good calibration kit again, the 3.5mm one. Now I'm trying to get rid of trace 2, 3 and 4 because now the signal generator is changing. First it's applied on port 1 and then it's changing to port 2. But if I delete those traces, only port 1 is sweeping. So we get rid of port 2, which means that our sweep time is now reduced to the half, to approximately 1 second. And we can now see here, this is our match. It's a really good broadband match. And if we plug it off, and this is now S11 up to 26.5 GHz. And as you can see here, this Smith chart looks way better than with the self-made calibration kit. And now I will just plug in a 120mm long transmission line. And now you can see a lot of circles here. And with the marker we can find the starting point, again here at the open point. And now here at about 1.35 GHz, we can now calculate the length of our trace, but this is not the TDR itself. For this we can go to trace config, time domain, and activate the time domain. Or we use the predefined macro, which we find here in application, TDR setup, TDR, and here we select the single calibration because we just calibrated port 1, so we can just use S11, not S21. Clicking on next, just selecting one measurement option, finish with fixture compensation, leading to the option to make an offset correction, but our calibration plane is already located here, so we will see the SMA connector plus the trace connected to it, so we can just close this window. And here we have our TDR result. On the x-axis now we have the time, and on the y-axis we can see the reflection coefficient in units, so 0 unit, -1 unit, +1 unit. Meaning that here we have a 50 ohm system. And this here is our SMA connector. And here we can see the open of our trace. And we can change the representation here by pressing measure. Then we're depicting the Z parameters again, the impedance parameters. And then just rescale the whole thing from 30 ohms to 70 ohms. And what we can see now is this is internal, so this is the VNA itself. Then here we have our SMA connector. Then here this is our trace, and it's really good 50 ohms wave impedance here. And then here we have our open at the very end. With the markers we can also locate those points. At 0 seconds, here, this is where our SMA connector begins. And then let's activate the second marker and this is here after 1.36 nanoseconds. Here our open begins. And now with this data, we can again calculate the length of our trace. And now I'm also changing the x-axis and stopping at 2 nanoseconds. And now I would like to show you what happens if I short the trace here in the middle. And then you can see the impedance goes down to 0 ohms. So this is the last experiment for the tutorial today. So here we have the same PCB with the same trace, but this time I did a bad job at soldering. So here I didn't solder it carefully. On the back side I completely forgot to solder the back side here, and even you can see a tiny air gap between SMA connector and the trace here. And now let's connect it to our TDR and let's check the difference between this trace and the trace before. And our bad soldering job can also be observed here with the TDR. So as you can see here, it's just a very simple PCB, just a transmission line, and we can now export this project as ODB++ file, and we can just need to hit the OK button. And then in your Altsum design directory, you will find the project output as a zip file, here the ODB++ file. And you can now import these files in CSD. And here is it. This is our transmission line. The trace is about 2.2 millimeters wide. Yes, that's correct. And we have a spacing 0.8 millimeters, exactly as we have set it up in Altsum Designer. And then we can also check if our trace is directly on the substrate. Yes, here we have no spacing in between. Then the substrate, if I remember correctly, is set with 1.6 millimeters. Exactly. And then the substrate should be connected directly here to the bottom ground plane. Exactly, 0 millimeters difference. Okay, so the import worked well. And now we need to set up our ports. So we just face our plane here. Then I just need the numbers for our waveguide port using this macro. Let's calculate it to get this extension coefficient, creating a new parameter with that expression. And then I would like to create the waveguide port here with this factor times the height of our substrate. And then here's our first port, and then just want to make our second port here on this side. Let's check everything. So we have here our structure with the top plane, with our bottom plane in purple. This is the substrate here. And in red we have our vias. So the next step is to set up the simulation. So let's take the frequency domain solver from 0.1 gigahertz, 100 megahertz up to 1 gigahertz. And before I run the simulation, let me just also enable the field monitors, the E field monitor and an H field monitor. They are now here. So let's set up our simulation and just click on the play button. And now we need to wait a few minutes until the simulation finished. Okay, the simulation now finished. It took a few minutes, and this is the reason why I've tried to keep the layout here as simple as possible. We can find the results here, our 1D results. We can check our S parameters here. And so S11, for example, so which means that most energy applied on port 1 will not get reflected. This is good. And S21, so the energy applied on port 1 gets transmitted to port 2. Here we can check our impedance, our wave impedance. It's a little bit higher than 50 ohms, but quite close. Check how many simulation points we have. Okay, here 1, 2, 3, 4, 5, 6 simulation points. What's also nice to see are the 2D results. And for example, let's take here a look on the electric field. So we can see here electric field of our microstrip line when the energy is applied on port 1. And we can run a nice animation here. And this looks good. So the electric field here pointing from the microstrip downward to the ground plane and vice versa depending on the phase. And we can also apply this simulation for the magnetic field. And this is also a nice animation where we can see how the magnetic field is here propagating. And we can also take a look on the surface current. And also here we can start an animation for the frequency of 550 megahertz. It looks like this. So we can see how the current is, the surface current is flowing here. So this is the end of this tutorial today. I hope I was able to give you a quick overview on how to work with a vector network analyzer. And if you're interested to dig deeper into the fascinating world of RF engineering and electromagnetic compatibility, feel free to come to our university and have a chat with some of our experts. For example, Professor Michael Gadringer, he's a real expert with devices like this one here, or with Professor David Pomerenke, he's a real expert in EMC. Thank you very much.